Your local MCP server works perfectly on your machine, but how do you safely expose it to remote HTTP clients while preserving all protocol features? We'll create a fully compatible FastMCP proxy server that bridges transports by wrapping a properly configured ProxyClient instance. The pattern maintains complete MCP protocol support, including tool registration, sampling, elicitation, and progress reporting, while handling the transport translation through explicit run parameters. Hash bridge local server to HTTP. Local proxy equals FastMCP as proxy. ProxyClient, local server pi. Name equals local to HTTP bridge. Hash run via HTTP for remote clients. If name equals main. Local proxy, run transport equals HTTP, host equals 0, 0, 0, 0, port equals 8080. This demonstrates the proxy server pattern in FastMCP, creating a transparent intermediary that forwards all MCP protocol operations to a backend server while maintaining identical interface behavior. The pattern enables transport bridging between different communication protocols, allowing a local server to be exposed via HTTP or other transports without modifying the backend implementation. The distinctive capability is how it preserves full MCP protocol compatibility, including tools, resources, and advanced features, while handling all transport translation through explicit configuration. The approach works by creating a FastMCP proxy server that wraps a properly configured ProxyClient connection to the backend. When clients interact with the proxy, it automatically forwards all operations while maintaining session isolation for concurrent requests. This design keeps transport concerns completely separate from business logic, with the proxy handling protocol translation based on its configuration. The resulting server appears identical to clients regardless of whether the backend is local or remote, and the proxy remains fully composable with other FastMCP servers through mounting operations. This pattern solves critical integration challenges when exposing local servers to remote clients or connecting systems using different transports. It enables seamless protocol bridging while maintaining full MCP compatibility, including advanced features like sampling, elicitation, and progress reporting. The explicit configuration requirement ensures predictable behavior, making it particularly valuable for production deployments where transport reliability and protocol consistency matter. The proxy can be composed with other servers just like regular FastMCP instances, providing flexibility in system architecture. Let's break it down line by line. Hash bridge local server to HTTP. Local proxy equals FastMCP as proxy. Creates a FastMCP proxy server that bridges between transports, wrapping a properly configured ProxyClient to forward requests to your backend service. This proxy pattern maintains full MCP protocol compatibility, including tool registration and client interfaces, while enabling transport conversion, here exposing local functionality via HTTP. The name parameter provides logging context, and proxies are fully composable with other FastMCP servers for complex routing scenarios. ProxyClient, local server pi. This initializes a ProxyClient that will forward requests to your local server implementation. The client requires proper configuration, typically a fully configured client object rather than just a file name, serving as the backend connection point for the proxy server. FastMCP's proxy pattern bridges transports, like local Python to HTTP, while preserving full MCP protocol compatibility, including tool registration and client interfaces. Name equals local to HTTP bridge. Sets a human-readable identifier for the FastMCP proxy server, used in logging and system introspection. This follows FastMCP's naming convention for composable components, ensuring consistent identification when combining multiple proxies or debugging transport bridges. The name becomes particularly important when composing proxy chains or integrating with mounted server components for advanced routing scenarios. This closing parenthesis completes the asProxy call, creating a FastMCP proxy server that forwards all requests to the configured ProxyClient backend. The proxy pattern enables transport bridging, here converting local MCP calls to HTTP, while maintaining full protocol compatibility including tool registration, client interfaces, and composability with other FastMCP servers. The ProxyClient requires proper configuration, not just a file name, and delegates execution transparently, appearing identical to clients regardless of the underlying transport protocol. This approach is particularly useful for protocol bridging, remote access, or service composition as documented in FastMCP's architecture.
Hash run via HTTP for remote clients. If name == main.
Standard Python entry point guard ensures the HTTP server only launches during direct script execution, not when imported as a module. This pattern is critical for creating reusable components that won't accidentally start network services when used as dependencies.
Local proxy. Run transport =HTTP. Host =0, 0, 0, 0. Port =8080.
Launches the FastMCP proxy server that bridges between HTTP transport and your local FastMCP backend, using asProxy to create a fully protocol-compatible intermediary. The ProxyClient requires proper configuration, not just a file name to establish the backend connection, while transport =HTTP enables HTTP protocol support without losing MCP features like tool registration and client interfaces. Binding to 0, 0, 0, 0, 8080 exposes the proxy to remote clients while maintaining composability with other FastMCP servers through the mounted server component. Transport bridging pattern. FastMCP's proxy system creates transport-agnostic connections between clients and backends, enabling seamless protocol translation between different transports like SDDO and HTTP. ProxyClient requires explicit configuration with a valid client object, not just a file name string, to establish the backend connection. The mounted server component enables full composition of proxies alongside local servers using identical mounting patterns.
The bridge that carries all protocols carries none of its own.